AB Calculus, section 5.4, page 1. Okay, so I would like you to use a calculator to evaluate each integral. The wording wrong up here, so we're going to have to fix that. To evaluate each integral. Express your answer as an improper fraction. Okay, please pause the video and go ahead and do that right now on your calculator. Evaluate each of these using FNINT. Please do it. Shut off the video. Go through and evaluate those. Welcome back. And we are looking at this information, confirming that you just did this on your calculator and got these numbers. For this integral from 1 to 0 of x squared dx, you should have gotten 1/3. For this one, 8/3. For this one, 9. And this fourth one, 64/3. And the fifth one, 125/3. All right, all of these are something over 3 with the exception of this third one. Let's go ahead and rewrite that so that it looks like the same format. So let's write that as 27/3. Now, when you look at these all pattern-wise, notice that all of them are something over 3. So all of these are something over 3. And then we notice that these are all perfect cubes, 1, 8, 27, 64, 125. And it happens to be this upper bound that got cubed. So we could write this as x cubed over 3, where that number that gets cubed is the upper bound. All right, now using these values, not your calculator, please find the value of the integral from 2 to 5 of x squared dx. And we notice that we can find the integral from 0 to 5 of x squared dx and subtract off the integral from 0 to 2 of x squared dx to get the integral from 2 to 5. That gives us 125/3 minus 8/3, which is 117/3. All right, now if we cover up that line right there and we look at how we could get from that integral right here down to this answer, kind of using this concept, notice what we did is we took this something cubed over 3 and we have the upper bound cubed over 3 minus, and then this 8/3 is the lower bound 2 cubed over 3 to give us that 8/3. Do you see that pattern? So we did this x cubed over 3 and evaluated it at this upper bound, and then subtracted that x cubed over 3, evaluated at the lower bound. When we do this, what I want you to think about, though, is that the derivative of x cubed over 3, or 1/3 x cubed, is x squared. And the antiderivative of x squared is x cubed over 3. So what we essentially did up here is we took this x squared, we did the antiderivative of it, which got us to x cubed over 3, and then we evaluated that x cubed over 3 at the upper bound minus the lower bound. That concept is called the second fundamental theorem of calculus. There is a first fundamental theorem of calculus, and we are going to do that after we do this second fundamental theorem. And this second fundamental theorem tells how to evaluate a definite integral by hand, i.e. no FNINT. So you'll be able to do these things now without your calculator. And following through, if g of x is the antiderivative of f of x, then the integral from a to b of f of x dx is All right, so we need to do the antiderivative of this f of x. So the antiderivative of f of x is this g of x. And then we'll need to evaluate that at that upper bound minus the lower bound. That is the second fundamental theorem of calculus. All right, now let's go ahead and use that second fundamental theorem to evaluate a few problems here. Looking at this first one, the integral from 0 to 2 of 2x minus 3. First thing, we're going to anti-differentiate this 2x minus 3. That's x squared minus a 3x plus a c. The notation we use to show that we're going to evaluate that is like this, with one single square bracket, 0 to 2. Now let's plug in the 2. That'll give us 2 squared minus 3 times a 2 plus a c. Then let's subtract off, plugging a 0 in here, 0 squared minus 3 times 0 plus a c. Simplifying, 4 minus 6 plus c minus, this gives us just a c, and we end up with negative 2. Notice the c's canceled out, and that will happen every time, because when you evaluate this antiderivative at that upper bound, you'll have a plus c. When we evaluate that at the lower bound, we have another plus c, but that lower bound one is being subtracted, so those c's will always subtract out. That tells us that we don't need to write it. That plus c will always subtract out. So there is no need to write plus c when evaluating a definite integral. Now, a definite integral is one that has bounds. So we've got this 0 and 2 bounds up here. All right, let's take a look at this next one. And we'll do the integral from 2 to 1 of 1 plus x over 2 dx. All right, so do an antiderivative here, and the antiderivative of a 1 is an x plus, now think of this x over 2 as 1/2 x. Now do an antiderivative. The exponent before doing a derivative must have been a 2. Pulling that 2 down here, 2 times something right here gives a half. That's got to be a fourth. And remember, we're not writing that plus c. We're going to evaluate this from 2 to 1. It does not matter that the lower bound is numerically bigger than the upper bound. We still substitute in the upper bound first. So we'll have 1 plus 1/4 times a 1 squared minus, sub in a 2, 2 plus 1/4 times a 2 squared. We have 1 plus a 4th minus 2 plus a 1 gives us 1 plus a 4th minus a 3. So we have negative 2 plus a 4th, negative 1 3/4, or improper fraction, negative 7/4. Thank you for joining me. Please join me on page 2.